All right, so how can we actually do this dimensionality reduction and find these r-dimensional bases that can represent our data in the best way? Principal component analysis, or PCA, is a method that can actually do that for us for linear relationships. So we can find the directions that when we project our data onto that direction, we are going to have the minimum possible error, or in other words, we are going to see the maximum possible projected variance in our data. The direction with the largest projected variance is called the first principal component. And then we can have multiple other directions, like D orthogonal directions in our D-dimensional space, right? The next direction after the first direction that captures the second largest projected variance, that is going to be called the second principal component, etc., etc. So basically, principal components are directions or dimensions that capture the most variance in our data, and we can order them. We can order them and we can say U1 is the one that captures the maximum variance, U2 is the one that captures the second maximum variance, U3, etc., etc., UR, etc., etc., until UD, right? And what we do in PCA is that we just select the first R ones to reduce the dimensionality from D to R. And then we can say that combined, for example, the direction U1, U2, U3 until UR can represent some variance, for example, 90% of the 90% of the data variance for us. Okay, so basically, this is what PCA does. Now, mathematically, PCA is actually a linear transformation or a rotation of the points that we had. So you remember that when we had these directions U1 and U2, it's as if we are rotating the axis here, as if we are rotating the axis from E1, E2 to U1 and U2, and we're representing our data in this new rotated axis, or we are having a linear transformation of our data. Now, you remember that when talking about the covariance, when we looked at the covariance matrices in the data, for example, in the 2x2 case, we had this. We had the variance of direction 1 or dimension 1, variance of dimension 2, and then the covariance between dimension 1 and 2. And what PCA does is that it rotates the points such that this covariance disappears as much as possible. So instead of the original covariance, we are going to have a new covariance in which the sigma 1, 2 and sigma 2, 1 are going to be equal to 0. And we are only going to see the variances. And the variances are actually going to be equal to the eigenvectors. So that is going to be represented as a diagonal matrix lambda for us. So we are going to see all of that pretty soon, but let's see what does this mean when we have some data points and we are trying to project our data points into, for example, 0 dimensions, right? So suppose that I have these two x1, x2, these are my data points in the original two-dimensional space, and this is E1, this is E2, right? And my goal is to find a zero-dimensional projection of my data such that I have the least amount of error. So when I project my data points into this zero-dimensional space, I have minimum of error. You remember that when we projected, the error was actually equal to the data point, the vector of data point, minus the vector of projection, right? Xi prime. That for each of our data points. Now, if I have n different data points, I can say that I want to minimize 1 over n summation over all of my data points. So an average error that I'm getting for each of my data points, I want to minimize that. Now, if I have a zero-dimensional new space, it's going to be a dot, right? And the projection of all of my xi's onto this dot is going to be the same, have the same value of xi prime. They are all the xi primes are going to be equal to the same coordinate. Let's call that m, right? So minimizing this is basically, if this is m, is going to be equivalent to minimizing 1 over n, y equals to 1 to n, vector xi minus vector m, right? And we are minimizing the lengths of these vectors. So let's take the norm. So if I want to find, so my basically problem is to find the m that minimizes this equation. If I have a function and I want to find the value of a parameter that minimizes that function, one way to do that is to take the gradient of that function with respect to that variable and set it to 0, right? So let's call this SSE, or the sum of squared error. What we can do is that we can take the gradient of sum of our squared error with respect to m, and we set it to 0, and then find the m that the sum of squared error is 0 in it, and that would give us the minimum, right? So for example, if this is my SSE, and these are different values that m can take, at this point, m is the minimum in which the gradient of SSE function with respect to m is 0. To take the gradient of this function, I can use the chain rule. So what is the chain rule? Regularly, our chain rule is going to look like this. The gradient of yr with respect to x is going to be equal to ry, r minus 1, gradient of y with respect to x, right? So here, we use the chain rule. Another way is we can say the gradient of f of g of x with respect to x is equal to gradient of f of x with respect to g of x multiplied by gradient of g of x with respect to x. So using this, if I take the gradient of SSE with respect to m, you can try it at home, I'm going to get to minus 2 over m, n, sorry, because we have 1 over n there, minus 2 over n, sum of xi minus m, I equals to 1 to n. This is the vector derivative. So you can check your linear algebra and review vector derivatives. Now I set this to 0. So I'm getting minus 2 over n sigma I equals to 1 to n xi minus m is equal to 0. As a result, what I'm getting is that 2 over n sigma xi, I equals to 1 to n. I can take m out of it, right? It's equal to 2n over n multiplied by m. Why? Because n times summing m is going to be equal to n multiplied by m, right? So basically, if I just move this, I will conclude that m is equal to 1 over n sigma xi, I equals to 1 to n. Okay, so this m is the zero-dimensional projection, the best zero-dimensional projection that I can get when I have n data points in my data. Okay, doesn't this look familiar to you? Yes, it does. M is actually the mean of my data. So what we have concluded from this is that the best zero-dimensional projection for your data points, for your d-dimensional data points, is going to be the mean or average of your data. Okay. What if we have a one-dimensional, we want to have a one-dimensional projection? If I want to have a one-dimensional projection, my problem is going to look a little bit different, right? So instead of this orange dot, I'm looking for example, this purple line that can represent my data. So I want to find U1, direction U1, that the projected variance of my data is maximized. Okay. Just a reminder that x prime was projected x on U1, okay? So we want to find U1. What is the direction U1? Now let's assume that we can assume that our data is centered, meaning that we are working with Z, or we can assume that only the direction of U1 matters, because variance really doesn't change no matter if the data is centered or not. So let's assume that U1 is going through the origin of the space. And U1 is also assumed to be a unit vector. Okay, so usually people center the data when they are working with. Now, x prime, sorry, which is the coefficient of the projection, is going to be equal to x, our original x, dot this U1 divided by U1 dot U1. And as a result, in the direction of U1, right? This is the value of coefficient, but we want it to be in the direction of U1, right? So this is going to be our x prime. Because we are assuming that U1 is a unit vector, this is basically is equal to 1. So our x prime is going to be equal to x U1, U1, right? So basically, U1 transpose. So basically our direction of our x prime is going to be a vector in direction of U1 that is scaled by the value that is the dot product between x and U1. Okay. Now, our goal is that we want to find the U1 that the projection, the variance of projection of x on it to be maximized, right? So we want to find the U1 that is going to maximize the projected variance. What do we mean by that? What we mean is that if our data looks like this, then if I have this U1, the variance of my data in this direction, for example, my data starts from here and ends to here, is the maximum. And for example, this is more than the variance of my data in this direction, which ranges from here to there, right? So the variance that I'm seeing, the stretch of the data is maximum in the direction U1. Now, because my goal is to maximize the projected variance, let's see what is the projected variance, right? What is this thing that I want to maximize? You remember the variance formulation, right? The variance formulation was on average 1 over n. How much our data varied on average? So 1 over n, sigma of I equals to 1 to n. How much our data varies compared to the mean of our data, right? So basically, if I am looking at my new projected data, which is xi prime, minus the mean of this projected data, let's call this mu prime squared, this is the variance that I get after the projection, right? This is the projected variance. Okay, so what I want to do is to find a U1 that maximizes this projected variance such that U1 transpose U1 is equal to 1, right? So because we said that we are assuming that U1 is a unit vector, so only the direction matters. Okay, so we know already that this projection of each of our data points is actually xi prime is actually equal to U1 transpose x, right? Also, you can easily see that the projected mean of our data is actually the mean of projection. So mean of projection is actually projection of mean. So this is equal to U1 transpose mu, mu being the mean of our original data in the original space. So what we want to do is we want to find the U1 that maximizes 1 over n sigma U1 transpose xi minus U1 transpose mu squared, I equals to 1 to n, such that U1 transpose U1 is equal to 1. This is our problem that we want to solve. So this is equal to 1 over n. We can just take U1 transpose is shared here, right? U1 transpose the vector of xi minus mu squared, which is basically, we can rewrite that like this. We can rewrite it in a vector form, which is equal to 1 over n, sigma I equals to 1 to n, U1 transpose xi minus mu multiplied by U1 transpose xi minus mu transpose, which is equal to 1 over n, sigma I equals to 1 to n, U1 transpose xi minus mu xi minus mu transpose U1. Okay? So what we can do is that we can take a look at these two and first multiply these two together and then multiply these two, right? So basically that is equal to 1 over n, sigma I equals to 1 to n, U1 transpose xi minus mu xi minus mu transpose U1. Okay, here U1, it doesn't depend on I, right? It's just with respect to I, it's constant. So what we can do is that we can take U1 out of this sigma from both sides. So we can have 1 U1 transpose here multiplied by 1 over n sigma I equals to 1 to n xi minus mu xi minus mu transpose, and then we can take this one out also, multiply by U1. Now, this guy here in the bracket, it also looks familiar to us, right? It is actually the covariance of our data, our original data. So basically this whole thing is equal to U1 transpose sigma U1. Okay, so we started from the projected variance and we saw that maximizing the projected variance is equivalent to maximizing this term such that U1 transpose U1 is equal to 1. Okay. So let's see what it means. So to solve this, what we can do is that we can say, when we do have this kind of optimization problem, in which we have this original optimization function with a constraint like this, we use something called Lagrangian multipliers to represent both of these two terms in the same optimization function or objective function. So what we do is that we say we want to maximize this one, so such that U1 transpose U1 is equal to 1. This problem is equivalent to maximizing, so finding a U1 that maximizes U1 transpose sigma U1 minus a multiplier called Lagrange multiplier alpha U1 transpose U1 minus 1. Okay, so this is the objective function that we have to solve. Now, to solve this objective function, we can do this. We can, again, take the derivative and set it to 0, solve for u1 to be able to get that, right? So far, we have seen that to find the u1 that maximizes the projected variance, we have to find the u1 that maximizes this objective function. Again, we are looking at the covariance here, right? So we are looking at the covariance of the original data. So it means that the maximization objective depends on the covariance of the original data. Okay, so now going to this place, we said that to find the optimum value of u1, we can take the derivative of this objective function that we have found and set it to 0 and find what u1 is going to be. So let's do that. So let's call this j, this function, j of u1. Take the derivative of j with respect to u1 and set it to 0 so we can get u1. Okay, so if we do that, we will see that this one, the left-hand side term, the derivative with respect to u1 is going to be equal to sigma u1, and the derivative of this one is going to be minus alpha u1. And we set it to 0, it's going to be like this. So we get to this equation that actually sigma u1 is equal to alpha u1. So u1 is a vector that multiplying this vector with the covariance matrix, it doesn't change the direction of this vector, do anything like that. It just scales this vector with a multiplier alpha. So the direction of u1 doesn't change as a result of multiplying u1 with the covariance matrix, but it just scales larger or smaller, right? Okay, that's an interesting result that we have. This formulation in general is the formulation of eigenvalue-eigenvector decomposition. So alpha is going to be the eigenvalue of the covariance matrix sigma, and u is going to be the eigenvector of it. Another thing that we can do is that let's look at what happens when we multiply both sides of this equation with u transpose. So if I multiply u transpose with both sides of it, u1 transpose, what I'm going to get is this, u1 transpose sigma u1 is equal to u1 transpose alpha u1. And u1 transpose alpha u1 is basically, because alpha is a scalar, is going to be alpha u1 transpose u1, right? We have seen it was a constraint in our optimization problem that u1 transpose u1 is actually equal to 1, right? So we get to this conclusion that u1 transpose sigma u1 is actually equal to the number alpha. All right? So basically, we get to this one. Now, what is this value, U1 transpose sigma U1? We have it here, right? U1 transpose sigma U1 is actually equal to the projected variance. It's equal to the variance of the projected data. So what it means is that to maximize this projected variance, what we have to do is to find the maximum alpha, right? So basically, also we know that alpha is the eigenvalue of the covariance matrix. So it means that to maximize the projected variance, we need to find the largest eigenvalue of the covariance matrix of our data, and then the direction that maximizes the projected variance is the eigenvector that is associated with its maximum eigenvalue. The maximum eigenvector, the eigenvector that is associated with the maximum eigenvalue, is called the first principal component for us. So the first principal component, which is the eigenvector that is associated with the maximum eigenvalue of the covariance matrix in the data, is the best direction, best one-dimensional direction that we can project our data into. So for example, here in our iris data, U1 is the direction that is the first principal component of the covariance matrix of our data. So far what we have looked at was the maximum variance way of looking at the problem, right? We can have another view of this problem, and that is the minimum squared error approach. The same way that we calculated the best projected zero-dimensional projection that gave us the mean, right? We can do that for the one-dimensional data also. So here, if we take that approach, the mean squared error of the projection is basically equal to the average of the norm of the error vectors that we get if we project our data into this one-dimensional direction. So what is the error? The error is the difference between our original data points and their projections, xi primes, right? If we expand this, we are going to actually get to this formulation. I encourage you to do this at home to achieve to this formulation. And let's see what it means. So what it means is that our goal is to minimize the error, right? So we want to minimize this MSU. And this is equal to some value here, which is a positive value, minus U transpose sigma U. U transpose sigma U, which is the variance that we have seen in like the projected variance that we wanted to maximize before. You remember that, right? We know that this is a positive value, so when we want to minimize MSE, we have to maximize this thing that is subtracted from the first term here. What is our first term here? Our first term here is basically the average of our data, right? This is the first term that we are seeing. So it is always fixed for a data set, right? It doesn't matter if the direction of U is U1 or U2 or any direction. This value is always fixed. U transpose sigma U, on the other hand, should be maximized. We should select the direction U that maximizes this so that we can get to the minimum possible MSE. So again, we achieved the same formulation to get the direction u that minimize the mean squared error. We have to find the direction u that maximizes the projected variance of our data. So that's how they are equivalent to each other. At the same time, this value here, we assume that our data is centered, right? So this value here, if our data is centered, is actually equivalent to the variance of our data set. The variance of our data set is, we have seen it before, that is equal to the trace of our covariance matrix, right? So our covariance matrix was like this. It was like sigma 1 squared, sigma 2 squared, etc., sigma d squared, sigma 1, 2, 1, 3, 1 d, same here, right? This was our covariance matrix. And the trace of this covariance matrix was the summation of diagonal values. This is equal to this trace. And what we are looking for is the direction that minimizes MSE and maximizes this projected variance, right? So minimizing MSE is equal to minimizing variance of our data minus the projected variance. We know that the projected variance is actually equal to the value of the first largest eigenvalue. So basically, what we are going to see is that the error that we are having is equal to the variance of our data minus the variance that we get because of projection, right? So the larger the eigenvalue is, the lower the MSE is going to be. So that is for the first one-dimensional, the best one-dimensional projection of our data. Okay. Now, how about the best two-dimensional approximation? The best two-dimensional approximation is that, well, we know that the first best dimension is the one that gives us the maximum eigenvalue, right? The second best direction is the one that gives us the second best or the second largest eigenvalue. So then, instead of only projecting onto U1, we can put the eigenvectors U1 and U2 next to each other and create a matrix U, U1 being the first principal component and U2 being the second principal component. And then for each of our data points in the dataset, we can use this matrix U to project our data into its new coordinates. So similar to previous projections, our new coordinates are going to be this U transpose multiplied by the original coordinates xi. Now this time, the total projected variance using these two dimensions is going to be equal to U1 transpose sigma U1, so the variance that is kept by projecting in the first dimension, plus U2 transpose sigma U2, the variance that is kept by projecting on the second dimension, which is equivalent to the first eigenvalue of sigma plus the second eigenvalue of sigma. And the error that remains by projecting our data into these two dimensions, the error that we are going to get this time is going to be equal to the variance of our data minus the variance of the projected data, which is basically lambda 1 plus lambda 2, right? So let's see an example here. Our iris data, if we want to find the optimal best two-dimensional projection of our iris data, it's going to be this. So this is U1, which captures the maximum variance in the data. This direction is really the stretch of the data that the data varies the most. And then the second one is U2, that is the stretch of the data that the rest of the variance lies in, right? So with this plane, we get a lot of things in order. Now, if we look at a non-optimal projection direction, for example, if we project our data into this plane here, we can see that the errors of our projections are going to be way larger than the errors that we get from this projection here. Okay. Now we have seen the best 0, 1, and 2-dimensional approximations. The best R-dimensional approximation is also similar. So the best R-dimensional approximation is going to come from the largest R eigenvalues of the covariance matrix, sigma. And you remember that at some point we said that sigma is a positive semi-definite matrix, right? So we said that the eigenvalues are all going to be non-negative, larger than or equal to 0, and we can sort them from the largest to the smallest. So we can have lambda 1, lambda 2, until lambda d, that they are all larger than or equal to 0. So if we just pick the first lambda 1 to lambda r, the first largest r eigenvalues, and we select the corresponding eigenvectors u1 through ur, then that is the best direction that we can project our data to keep the maximum variance in it. So ur, which is our projection matrix, is going to be the r-dimensional basis vector matrix that is going to preserve the maximum variance and give us the least error when we project our data into. We can create the projection matrix PR by multiplying UR with UR transpose, right? And the variance of our data that is going to be kept is going to be equal to the summation of these eigenvalues. So the projected variance. And then the error that we are going to have is going to be, again, equal to variance of our data minus the variance that we are going to be keeping by the projection. So minus this summation of lambda i's from 1 to r. But also note that the variance of our data is actually equal to the summation of all eigenvalues from 1 to d. So basically, the error that we are going to have eventually by the projection is equal to the summation of all the eigenvalues from 1 to d minus the summation of eigenvalues from 1 to r. Or in other words, it's going to be equal to the summation of eigenvalues from r plus 1 to d, right? Lambda. Now, what this means is that when we are choosing these R dimensions, our new directions U1 to UR, we are basically throwing away another set of directions from R plus 1 to D that could have explained our data. But because we are choosing the directions that have the minimum variance, these are like giving us the least error possible, which is this value. Now, how can we choose how many dimensions we need to represent our data in the best way possible? Well, we can do that by expecting the variability that we want to represent in our data. So we know that, for example, if I choose the first R directions, I'm going to see 90% of data variance. If I choose from 1 to R plus 1, for example, I'm going to see 95% of the variance, etc., etc., and we are going to choose according to that. In other words, I know that the total variance that I'm going to keep by doing the projection is the summation of lambda i's from 1 to R. And I know that the total variance that exists in my data is the summation of eigenvalues from 1 to D. So I can actually calculate the fraction and see what percentage of my total variance I'm going to keep by projecting into the first R principal components. And then I can decide based on that. So for example, I can say I want to have a dimensionality reduction that can keep 90% of my data variability. So meaning that this fraction that I have here, I want it to be more than or equal to 90%. Because the variance of the data is something that I can easily calculate, and the lambda i's also, I can calculate what values they have. I can try different values of R, and I can add the dimensions to the projection dimensions until I get to this value of 90% or more. And then I would say, okay, that is enough. I'm going to stop at this point. So basically, we are going to stop at the smallest value R, such that this fraction is larger than or equal to the threshold that we are going to set for the total variance that we are going to keep. Okay, so let's see the algorithm for PCA, or principal component analysis. When we are given a D, which is our data set, and an alpha, which is the threshold that we want to keep the variability that we want to keep. Like, for example, 95% of our variability we want to keep. The algorithm is like this. First, we are going to calculate the mean of our data, and we are going to center our data. This just makes the computations much easier. So we calculate Z. Now we calculate the covariance of the Z matrix, so the covariance of our data, and we calculate the eigenvalues and eigenvectors of our data. So now I have all of the D eigenvalues and D eigenvectors. And I start to calculate the fraction of variance for different values of R. If I keep 1 dimension, 2 dimensions, 3 dimensions, etc., etc. And then I'm going to choose the smallest R that give me the fraction that is more than that threshold alpha that I used in my input. So the f of R that is, for example, larger than or equal to 95%, which R is going to give me that. And then I'm going to select those first R eigenvectors, put them in a projection matrix U, and I can calculate the new coordinates for my projected data by multiplying this UR transpose with the original data vectors that I have, and return that reduced dimensionality data. For example, in our iris data set, suppose that we have this covariance matrix here. We can calculate the eigenvalues and eigenvectors of it. And suppose that these are my 3 values that I'm getting, lambda 1, 3.66, lambda 2, 0.239, and lambda 3 is this one. And then my three lower dimensional eigenvectors are u1, u2, and u3. Now, suppose that I want to see how much variability I'm going to keep by choosing each of the dimensions. Like, if I only want to stick with one lower dimensional data, lower dimension, I'm going to keep lambda 1 of the variability, right? So basically, the variance, the fraction of variance that I'm going to keep is going to be equal to lambda 1 over lambda 1 plus lambda 2 plus lambda 3. That is the fraction of variance for one dimension, right? Which, if we do calculate that, it's going to be equal to 0.925. So I'm going to keep more than 92% of the variability by just using one dimension. If I choose two dimensions, the two largest dimensions, this is the variability that I'm going to keep is going to be equal to lambda 1 plus lambda 2 divided by lambda 1 plus lambda 2 plus lambda 3. That is going to be this value, 0.985, which means that if I choose two dimensions, I'm going to keep more than 98% of my data variability if I project my data on both U1 and U2. And then if I project my data on all three of these dimensions, I'm going to not to lose any variance. So my total variance is going to be represented 100%. Now, suppose that I would like to have a lower dimensional representation of my data that keeps at least 95% of the variance. Okay, so how many dimensions should I choose? Well, because I need at least 95%, only one dimension is not going to be enough for me, because one dimension is only keeping 92.5% of the variability. So let's check the second dimension. If I choose dimension 1 and 2 together, it's going to be 98.5, which is more than 95%. So that is good enough for me. So we are going to choose both U1 and U2 and basically reduce our dimensionality to 2, and we are going to have more than 95% of the variance. So this is our iris data again. This rotation here shows the optimal three-dimensional basis. You can see that U1 is the one that keeps the maximum variance. After that, U2 is the one that keeps the second largest variance, and U3 is the direction that keeps the third largest variance in our data. Now, if we choose U1 and U2 only, we can project our data into U1 and U2, and these are going to give us the new coordinates or AIs in the new projection in the new dimensions or axis that we have. So geometrically, we have seen that when we are choosing these U1, U2, and U3, it's as if we are rotating our axis towards U1, U2, and U3 such that our data is represented with the maximum variance, and at the same time, the covariance between our data points is going to go to 0. So meaning that, you remember that our eigenvector decomposition formulation, right? This was the formulation that we had. Now, if we multiply both sides with, if you put together all the UIs and build this matrix, we are going to have this formulation, right? with all the UIs. And then if we multiply both sides with U transpose, and we know that U transpose is equal to U inverse of U, or U to the -1, because they are orthonormal, we are going to get to this formulation. So the covariance matrix is going to be equal to multiplication of three matrices: U, which is the eigenvectors all put together; lambda, which is a diagonal matrix. On the diagonals, we have eigenvalues, and everywhere else, we have zeros; and U transpose, which is the transpose of eigenvectors put together. So basically, it means that in this new space that we have, our covariance between different data points in the dimensions that are represented by U, they are going to be equal to 0, because our new covariance matrix is basically going to be this lambda, which on the diagonals we have lambda 1 through lambda d, and everywhere else, which was the covariance between each two dimensions, it will be 0. Okay, and if we look at this equation, X transpose inverse of sigma X equals to 1, we are going to see a d-dimensional ellipsoid, or hyperellipse, that basically shows the stretch of our data in each of the new directions that we have. So the eigenvalues of our covariance matrix is going to show us how stretched our data points are, in which direction? In the direction of eigenvectors of our covariance matrix. So like this. So basically U1, U2, and U3 are showing our new axes, right? And the equation that we have here, are going to show these ellipsoids around these directions that represent the stretch of our data. Elliptic contours in the bases that we are going to have. And you can look at it like this also. So this is when we have it in the original directions, and this is when we have it in the projected directions. Okay, the rotated one. All right, so that is how we reduce the dimensionality of our data using the principal components of our covariance matrix, or PCA, principal component analysis.